Hello students, welcome back to my channel. You are watching All Over Physics. Here we are starting a new course on class 11 and 12 physics. We are going to cover all the chapters of the book called Concept of Physics by H C Verma. As you all are aware, Dr. H C Verma's Concept of Physics stands as the pinnacle of conceptual learning for students venturing into the world of physics at the high school and early graduate levels, particularly by aspirants of prestigious exams like IIT JEE and NEET. So let's start with chapter 1, that is Introduction to Physics. But before proceeding further, please subscribe to my channel and like the video. Now I'll be walking you through the contents. We'll start with the introduction about the course, like how we'll study each chapters, understand theories, solving problems, and how the chapter is relevant for exams. Then we'll start with chapter 1's first topic, that is physics and mathematics. Here we'll get to know why mathematics is called the language of physics. Then we'll talk about basics of units and dimensions. Once theory portions are completed, we'll proceed with solved examples and correlate them with theory. Finally, we'll solve problems given at end of every chapter. Let's start with introduction about the course. I have arranged my lecture in 4 pillars. First comes the theory part, then comes the worked out examples. Both theory and worked out examples will go side by side. Then comes the third pillar, that is solving exercises problems, and the last pillar is homework. Physics theory forms the backbone of our understanding of the universe. While experiments help us observe and measure, it's theory that allows us to explain, predict, and connect those observations. From Newton's law to Einstein's relativity, theoretical physics have shaped everything from modern technology to our view of space and time. So we can say that theory is the backbone, and deep understanding of theory is required to understand physics. Therefore, we shall discuss in details about theories and concept of every chapter. Good knowledge of theories will be a game changer when it comes to excelling in board exams and competitive exams like JEE, NEET, etc. Because when it comes to competitive exams, time is limited and accuracy is everything. A strong grasp of theory allows you to solve MCQs faster because you understand the principles rather than relying on rote memorization. Along with theory, we'll understand worked out examples and correlate problems with learned theories. Once the chapter is completed, we'll solve every given problem. You all know the proverb that all is well that ends well. So you have to use your brain and test your knowledge by solving problems, which I'll give you at end of every chapter. I'm sharing my mail ID in the video description. You can mail your answers to me. So best of luck for your future endeavors. So let's start with chapter 1, that is Introduction to Physics. And first thing that we'll study is physics and mathematics. Physics is the study of nature and its laws. It is the science that explains how things move, work, and interact in the universe. As you can see in the screen, Newton is studying under an apple tree during his school closure days. Here, Newton got the idea of gravity when an apple fell on his head. So, falling of an apple is governed by laws of gravitation. Similarly, other phenomena like tide in the ocean, rotation of moon around the earth, all are governed by some laws of physics. Physicist Dr. Richard Feynman has given a wonderful description of what is understanding the nature. Suppose we don't know the rules of chess but are allowed to watch the moves of every player. If we watch the game for a long time, we may make out some of the rules. With the knowledge of these rules, we may try to understand why a player played a particular move. However, this may be a very difficult task. Even if we know all the rules of the chess, it is not so simple to understand all the complications of a game in a given situation and predict the correct move. Knowing the basic rule is, however, the minimum requirement if any progress is to be made. One may guess at a wrong rule by partially watching the game. The experienced player may make use of a rule for the first time, and the observer of the game may get surprised. Because of the new move, some of the rules guessed at may prove to be wrong, and the observer will frame new rules. Physics goes the same way. The nature around us is like a big chess game played by nature. The events in the nature are like the moves of the great game. We are allowed to watch the events of nature and guess at the basic rules according to which the events take place. We may come across new events which do not follow the rules guessed earlier, and we may have to declare the old rules inapplicable or wrong and discover new rules. Since physics is the study of nature, it is real. No one has been given the authority to frame the rules of physics. We only discover the rules that are operating in the nature. Aryabhat, Newton, Einstein, or Feynman are great physicists because from the observations available at the time, they could guess and frame the laws of physics which explain these observations in a convincing way. But there can be a new phenomenon any day, and if the rules discovered by the great scientists are not able to explain the phenomenon, no one will hesitate to change these rules. I have mentioned earlier that physics is the study of nature. Now we need to describe the nature. This description of nature becomes easy if we have the freedom to use mathematics. Let us understand the concept with the help of an example. Say we take the example of Newton's law of gravitation. Assume the apple which fell from the tree is having a mass of m2 and assume mass of the earth is m1. Then Newton says the force is proportional to the product of the masses and inversely proportional to the square of the distance apart. Therefore, I will write mass of the earth equal to m1 and mass of the apple is m2. Then according to Newton's law of gravitation, force between them is proportional to m1 m2 by r square. Now we can take a constant, that is g, which is nothing but gravitational constant, and we can rewrite the equation as force is equal to g m1 m2 by r square. Therefore, you can see the description of the law becomes easy and understandable when we are expressing them with the help of mathematics. So we can say mathematics is the language of physics. Having little bit knowledge about what is physics and how to describe physics, now we'll move to the next part, that is units and dimensions. In physics, we say that description is quantitative. These quantitative descriptions express physical phenomena using numerical values, units of measurement, and mathematical equations. So let us understand them with help of an example. Suppose a car is moving with a speed 10 meter per second. So we'll write speed of the car is 10 meter per second. So this 10 is the numerical value. Then comes meter per second. So meter, seconds, both are units of measurements. Now comes the mathematical equation. Like Newton has given the second in the second law, that is force is equal to mass into acceleration. So this is nothing but mathematical equation. To understand the quantitative description, we'll take help of an example. We can see an elephant and a goat in the screen. We know elephant is heavier than a goat, but question is how much heavier. Let us assume we have chosen a standard mass, calling it an unit mass. The elephant is 200 times the unit mass and the goat is 20 times of that unit mass. So we came to know with the help of that unit mass that elephant is 10 times heavier than the goat. Now assume we call the unit mass 1 kg. So the value comes to be 10 kg. So the numerical value in this case is 10 and the unit of measurement in this case is kg. In the previous slide, we have come across a new concept called unit mass. Now the question is how to define the unit mass. Different people can define unit mass differently. but then quantitative description will not be uniform. Therefore, there is an international body called CGPM with the authority to decide the units by international agreement. It holds its meetings, and any changes in the standard units are communicated through the publication of the conference. There are a large number of physical quantities which are measured, and every quantity need a definition of unit. However, not all the quantities are independent of each other. As a simple example, if a unit length is defined, a unit area is automatically obtained. If we make a square with its length equal to its breadth equal to the unit length, its area can be called the unit area. All areas can then be compared to the standard unit of area. Similarly, a unit of length and a unit of time interval are defined. A unit of speed is automatically obtained. If a particle covers a unit length in unit time interval, we say that it has a unit speed. So there comes a new concept called fundamental quantities. With the examples we just discussed, we can define fundamental quantities as: first, it should be independent of each other. Second, all other quantities may be expressed in terms of fundamental quantities. So, what should we call these quantities? These called derived, as they are derived from fundamental quantities using multiplication and division. Number of total fundamental quantities is only 7. All the rest are derived from them. CGPM held its meeting and they decided a system of units known as the International System of Units, which is abbreviated as SI. SI units are widely used throughout the world. SI unit matters because of its universality, consistency, and simplicity. There are 7 base SI units, each representing a fundamental physical quantity. The table shows the 7 fundamental physical quantities and their symbol of dimension. Now, what is the dimension that we'll learn in the subsequent slides? But just remember, when we mention dimension, we have to represent them by bracket symbol. So the 7 physical quantities are length, for which the symbol of dimension is L. Then comes the mass, which is represented by M. Then comes time, represented by T. Then is electric current with the representation of I. Then we have temperature theta, luminous intensity, that is J, and amount of substance, that is N. We have learned about the dimensions of the 7 fundamental quantities. Now we learn about their unit and their symbol. Coming to length, its SI unit is meter and it is represented by the symbol M. Similarly, mass is represented by the symbol kg and the unit is called kilogram. Time is second, represented by the symbol S. Electric current unit is ampere, represented by the symbol A. Then comes the thermodynamic temperature, which is represented by the unit Kelvin with the short form of K. Amount of substance unit is mole. And then luminous intensity, where the unit is candela and the symbol is CD. The 2 supplementary fundamental units that were historically part of the SI system are radian, which is the unit for plane angle, represented by the symbol rad, and steradian, which is the unit for solid angle and is represented by the symbol SR. Now the question is, what is a plane angle and what is a solid angle? Plane angle is 2D. It is the angle formed between 2 intersecting lines that lie in the same plane. Whereas solid angle is 3D. It is the angle that the circle makes at the center of the sphere. We can see there is a circle and there are 2 intersecting lines which is making an angle theta at the center and making an arc length of S. Therefore, we can write plane angle theta is equal to S by R. So where S is the arc length and R is the radius of the circle. Similarly, solid angle, which is represented by the symbol omega, is written by A by R square, where A is the area of the circle and R is the radius of the sphere. Now the question is why it was called supplementary and why it was historically part of SI system. They are supplementary because they represent geometric quantities, not physical quantities like mass or time, and they are ratios. So coming to plane angle theta, we can see arc length divided by radius. So if we write the units, then it is mass divided by mass. Therefore, it is a dimensionless quantity. Similarly, for solid angle, area is meter square and radius square is also meter square. So this is also dimensionless. Therefore, in 1995, the International Committee reclassified them as dimensionless derived units. They are no longer called supplementary units. SI units use prefixes to express very large or very small quantities. So we can see the table of all SI prefixes that are being used. So they are expressed in 10 power. So first is exa, that is 10 power 18. Then we have 10 power 15 peta. Tera is 10 power 12. 10 power 9 is called giga. 10 power 6 is mega. 10 power 3 kilo. 10 power 2 is hecto. 10 is deca. 10 power minus 1 is deci. 10 power minus 2 centi. 10 power minus 3 milli. 10 power minus 6 micro. 10 power minus 9 nano. 10 power minus 12 pico. Then femto is 10 power minus 15, and last is atto, that is 10 power minus 18. So these are all the symbols to represent them. So later these symbols will be very much useful, so you can memorize them. And day to day, there are few prefixes which are more familiar to us. Like when we talk about memory of your PC, then it comes to either tera or giga or mega or kilo. Then a few things when we talk about your processor, like what kind of chip you are using, then it's come either micro, then nano, then pico, etc. And these things like centi, milli, anyway, these are very useful. Deci, hecto also, this is very useful. So all the physical quantities of interest can be derived from the base quantities. When a quantity is expressed in terms of the base units, it is written as a product of different power of the base quantities. The exponent of a base quantity that enters into the expression is called the dimension of the quantity in that base, and an expression for a physical quantity in terms of the base quantities is called the dimensional formula. So we'll discuss in detail about these two things. First is the dimension, and next is the dimensional formula in the subsequent slides. To make it clear what we just told earlier, consider the physical quantity force. So in the figure, we can see there is a baseball player and he is trying to generate as much force as he can. This force is equal to mass time acceleration. Therefore, you can see force is equal to mass time acceleration. And acceleration is nothing but change in velocity divided by time interval. So therefore, you can write acceleration is equal to velocity by time. And velocity, on the other hand, is length divided by time. So rearranging, we can write force is equal to mass cross length cross time to the power minus 2. So you can see the dimension of force are 1 in mass, 1 in length, and minus 2 in time. Already we have learned that mass is denoted by symbol capital M, L is denoted, length is denoted by symbol capital N, and time is denoted by capital T. Therefore, altogether we can write F is equal to ml t to the power minus 2. Note that in this type of calculation, the magnitudes are not considered. Thus, the physical quantity that is expressed in terms of base quantity is enclosed in square bracket to remind that the equation is among the dimensions and not among the magnitudes. So to summarize, we can say this is the dimensional formula, and in the dimensional formula, force is having dimension of 1 in mass, 1 in length, and minus 2 in time. We'll take an example and we'll try to solve it. The problem is to calculate the dimension formula of energy from the equation is equal to half mv square. So dimensionally we can write energy is equal to mass into velocity. square. Now the half we are not considering because it is a number and number has no dimension. Now energy is represented by the symbol E, mass represented by m, and already we have learned that velocity is length divided by time, and there is a square, so we'll write square. Now we want dimension formula, therefore we have to use square bracket because the equation is among the dimensions and not among the magnitude, is equal to ml square t to the power minus 2. Therefore, the dimension formula of energy is equal to ml square t to the power minus 2. Till now we have learned about dimension and the dimensional formula. Now we learned about various uses of dimension, like the one we have mentioned in this slide, that is homogeneity of dimensions in an equation. An equation contains several terms which are separated from each other by the symbol of equality plus or minus. The dimensions of all the terms in an equation must be identical. This is another way of saying that one can add or subtract similar physical quantities. Thus, a velocity cannot be added to a force, or an electric current cannot be subtracted from the thermodynamic temperature. This principle is called the principle of homogeneity in an equation. So it is very useful to check whether an equation may be correct or not. If the dimensions of all the terms are not the same, the equation must be wrong. Let us understand homogeneity of dimensions in an equation using two examples. So first we'll take the first example, that is x is equal to ut plus half at square. So let us check the first equation, that is x is equal to ut plus half at square. But before we check whether the equation is dimensionally correct or not, we'll try to understand what the equation is trying to tell. So in the equation, x is the distance, whereas u is the initial velocity, a is the acceleration, and as we know, t is time. So the equation is trying to tell if a particle is starting with an initial velocity u and it is accelerating with a, then at time t, the distance traveled by the particle will be x. Now we'll check the dimensional homogeneity. So first is x, which is nothing but distance. So dimensionally we can write square bracket x is equal to L. Then the second part, that is ut, is equal to velocity cross time. And velocity, as we all know, is length divided by time. Then the equation, finally we can write it as ut is equal to length, that is L. Then comes the third part, that is half at square. Now half is a number, so it has no dimension. So we can write acceleration cross time square. Now already we have learned acceleration is velocity divided by time and velocity is length by time. So rearranging, we can write the equation as length by time square into time square. So again, what remains is the length is equal to L. So we can see in the equation, if we write it as dimensionally, it is nothing but L is equal to L plus L. So the equation is correct as far as the dimensionality are concerned. Now we'll test the dimensionality of the second formula, that is t is equal to 2 pi square root of m divided by f divided by x. So this is the equation of time period. In the later slides, we'll try to get in details how the time periods are derived. But now we'll try to check the homogeneity of the equation. So in the equation, t is the time. Then m is the mass, f is the force, and x is the distance. So dimension of time is t. In the left hand side, first we have a number. So number have no dimension. Now we have mass. So dimension of mass is capital M. Already we have learned dimension of force is ml t to the power minus 2, and dimension of x, that is distance, is L. So in the left hand side we can write as capital M divided by ml t to the power minus 2 divided by L. So the L will cancel out. What will remain is m to the power minus 2. And this also cancelled out. So what remains is t square, that is t. So we can see in the left hand side we are getting dimension t, and in the right hand side also we are getting the dimension t. So we can say the equation is correct as far as the dimensions are concerned. Next use of dimension is conversion of units. When you choose to work with a different set of units for the base quantities, the units of all the derived quantities must be changed. Dimensions can be useful in finding the conversion factor for the unit of a derived physical quantity from one system to other. Consider an example. When SI units are used, the unit of pressure is 1 Pascal. Suppose we choose 1 centimeter as the unit of length, and 1 gram as the unit of mass, and 1 second as the unit of time. This is still in a wide use and is called the CGS system. The unit of pressure will be different in this system. Let us call it for the time being 1 CGS pressure. Now the question is, how many CGS pressure is equal to 1 Pascal? Now we'll try to find the answer of the question, that is how many CGS pressure is equal to 1 Pascal. Now pressure is nothing but force divided by area. So dimensionally we can write pressure is equal to, within second bracket, force divided by area. Now already we have learned force is ml t to the power minus 2 and area is length square. So this is m l to the power minus 1 t to the power minus 2. Now we'll come to 1 Pascal. So already we have mentioned 1 Pascal. We have used mass in gram, then length in meter, and time in second. Similarly, 1 CGS pressure is equal to, here unit of mass is gram, then unit of length is centimeter, and unit of time is second. Therefore, we'll write 1 Pascal divided by 1 CGS pressure is equal to 1 kg divided by 1 gram into 1 meter divided by 1 centimeter to the power minus 1 into 1 second by 1 second to the power minus 2. So rearranging, we can write it as 10 power 3 into 10 power minus 2 to the power minus 1 is equal to 10. So we can say that 1 Pascal is equal to 10 CGS pressure. Now we'll come to another use of dimension, that is deducing relation among the physical quantities. Sometimes dimension can be used to deduce a relation between the physical quantities. If one knows the quantities on which a particular physical quantity depends, and if one guesses that the dependence is of product type, method of dimension may be helpful in the derivation of the relation. Taking an example, suppose we have to derive the expression for the time period of a simple pendulum. The simple pendulum has a bob attached to a string which oscillates under the action of the force of gravity. Thus, the time period may depend on the length of the string, the mass of the bob, and the acceleration due to gravity. Let us take an example. Suppose we want to derive the expression for the time period of a simple pendulum. So the pendulum has a bob of mass m, which is attached to a string from a rigid support, and it is oscillating under the force of gravity in the following manner. Thus, the time period may depend on the length of the string, the mass of the bob, and the acceleration due to gravity. We assume the dependence of time period on these quantities is of product type. Therefore, we can write time period is proportional to L, M, G. So taking a constant for equality, we can write T is equal to K, L to the power A, M to the power B, and G to the power C. So where A, B, C are the exponents that we want to derive. Now if we write the equation dimensionally, then in the left hand side it will be capital T. Since K is a number, therefore it has no dimension. Then comes the length L to the power A. Then mass is represented by capital M, so M to the power B. And G is nothing but acceleration due to gravity. So already we have learned that acceleration is represented by L t to the power minus 2 to the power C. So rearranging, we can write L to the power A plus C, M to the power B, and T to the power minus 2C. So this is the left hand side and this is the right hand side. Now we know that left hand side should be equal to right hand side. Now left hand side time has exponent of 1. Therefore balancing, we can write A plus C is equal to 0, B is equal to 0, and minus 2C is equal to 1. Rearranging, we can find that A is equal to half, B is equal to 0, and C is equal to minus half. Therefore, we can write the equation T is equal to constant L to the power half, B to the M to the power 0, and G to the power minus half. So therefore, it is M L by G to the power half. That is equal to K square root of L by G. Therefore, time period is equal to K square root of L by G. Thus, by dimension analysis, we can deduce that the time period of a simple pendulum is independent of its mass and is proportional to the square root of length of the pendulum and inversely proportional to the square root of acceleration due to gravity at the place of observation. So let's talk about order of magnitude. So in physics, we come across quantities which vary over a wide range. We talk of the size of a mountain and the size of the tip of a pin. We talk of the mass of our galaxy and the mass of a hydrogen atom. We talk of the age of the universe and the time taken by an electron to complete a circle around the proton in a hydrogen atom. So it is quite difficult to get a feel of largeness or smallness of such quantities. To express such widely varying numbers, one uses the powers of 10 method. In powers of 10 method, each number is expressed as a cross 10 power b, where a is greater than or equal to 1 but it is less than 10, and b is either a positive or a negative integer. To get an approximate idea of the number, one may round the number a to 1 if it is less than or equal to 5. Similarly, we can approximate the number a to 10 if it is greater than 5. The number can then be expressed approximately as 10 power b, where b is the order of magnitude. Let us take some examples. The diameter of the sun is 1.39 into 10 to the power 9 meter, and diameter of a hydrogen atom is 1.06 into 10 to the power minus 10 meter. Now we told in powers of 10 method, we express numbers in A cross 10 power B format. So here we can see A is 1.39 and B is 9. Now we told that we can approximate the number A to 1 if it is less than or equal to 5. So you can see in this case, A is 1.39, which is less than 5. Therefore, we can approximate it as 1 into 10 power 9. That is 10 power 9 meter. So we can see the diameter of the sun is of the order of 10 power 9 meter. Similarly, in the case of diameter of a hydrogen atom, A is 1.06, which is again less than 5. Therefore, you can approximate it as 1 into 10 power minus 10 meter. That is 10 power minus 10 meter. Therefore, the diameter of hydrogen atom is of the order of 10 power minus 10 meter. So we can say the diameter of sun is 9 minus 10, that is 19 order of magnitude larger than the diameter of hydrogen atom. We have completed the theory part of the first chapter. So let us summarize what we have completed so far. First, we have learned about physics and mathematics, where we have discussed about how physics is the study of nature and its laws, and why mathematics is called the language of physics. Then we came to the next part, that is units and dimension, where we talked about units and international body governing units. Then we talked about 7 fundamental quantities and how derived quantities are obtained from them. Then we got the idea about SI units and prefixes. Then we got familiar with dimensions and dimensional formula. After that, we have talked about various uses of dimension, like homogeneity of dimension in an equation, conversion of units, and deducing relationship among the physical quantities. Finally, we came to the last part, that is order of magnitude. All right, students, that's it for today's lesson. I hope you found it helpful and learned something new. We'll start our next video with understanding examples. If you enjoyed the video, make sure to hit that like button. And if you're new here, don't forget to subscribe to the channel for more physics content every week. Got any question or topics you like me to cover next? Drop me a comment below. I love hearing from you. Thanks for watching, and as always, stay curious, keep learning, and I will see you in the next video.